Okay, so now, so the first thing we want to do is look at this idea of a vector field. Now, a vector field you might think of as, well, there's all kinds of vector fields. There's velocity fields, there's gravitational fields. You can think of this room as a big vector field. Like, for one thing, gravity. There's the gravity pointing us down toward the center of the earth, right? There's all kinds of vectors all around us. And vector fields are how we mathematically model those things. Like, we might talk about a velocity vector field where you have a point, and then coming from that point is a vector where the magnitude of that vector is the speed, maybe. Okay? But let's just start off with a generic vector field in 2 space. Now, if we have R2, and let me pick a nice marker here. So we're looking at R2. Okay? Now, R2 is just when you have the x component and the y component. And when we talk about a vector field, we're talking about something like this. So we have f of xy. Now, this is different than the vector valued functions that we've looked at before. In the vector valued functions we looked at before, what we do is we put in a real number and we get out a vector. Now we're going to put in an ordered pair or an ordered triple, and we're going to get out a vector. And the way we plot these is a little bit different. So we have a function here. You know, I'm just elaborating on what I have up here. And then I have n, x, y, j. Okay? So this is just the generic way we might write a vector field in R2. Now, of course, in R3, so this is R2. In R3, of course, it might be something like this. And we might have m, x, y, z, I, plus n, x, y, z, j, and then, of course, plus maybe p, x, y, z, k. Okay? So if we're dealing with R3, we probably write it this way generically. Now, first thing I want to look at is, well, how do we represent a vector field? How do we evaluate a vector field? Now, by the way, this right here is a vector field. This is the model for this vector field. And it has no interpretation here. I'm not talking about a gravitational field, anything other than this is just a function. Now, let's suppose that for this particular function, we plug in, let's say a 1, 1, and let's suppose we get out, you know, maybe a 2 for the x-coordinate and a 3 for the y. In other words, m of 1, 1 is equal to 2, and n of 1, 1 is equal to 3. Now, here's how we plot that. We go immediately to this 1, 1, which is right there. That is our initial point for some vector. Okay? That's the initial point. From that point, not from the origin, but from that point, 1, 1, we're going to go over 2 and up 3. So I go over 2 and up 3. I guess right there, right? Over 2 and up 3, and that's our vector. Okay? So we put in an initial point, and it spits out a terminal point, and that's our vector. Okay? So we might have something like this. We might have 2 and negative, 2 and 1, and maybe it's going to give us 1 and negative 3. Okay? So we'd go over 2 and up 1, and now we're going over 1 and down 3. So over 1 and 1, 2, 3. So the vector would be like that. Okay? Any questions about that? Okay, so this idea is pretty simple. And whereas with a vector valued function that we looked at before, we put in a t, and we always are just simply looking at the origin as the initial point, and the terminal point would be what the vector, the function does. Now, you can see that if this could get very messy. So if we start trying to plot a vector field, in other words, I want to represent a vector field, that could get messy because there are literally an infinite number of points just in this little region here, right? there are an infinite number of points that I could plug in and get out a vector. Well, if there are an infinite number of points, there are an infinite number of vectors there, and it could get to be just a mess, right? You just got a big basket of vectors, and it doesn't tell you anything. So what you want to do when you're talking about plotting a vector field or represent a vector field graphically, you want to kind of be wise with how you choose your plots. You want to get an idea about what's going on with the vector field, but you're keep in mind, okay, there's a limited amount of plotting that I can do. Now, to illustrate, I've got this vector field here. F of xy equals negative yx. And here's what we can do. Okay, so we've got this vector field, negative yx, and I want to plot some vectors and try to get an idea about the behavior of this vector field. So here's what I want to do. I want to just start plotting some points, and I want to choose the points this way. I'm going to start off plotting vector. I want to start off putting in points so that the magnitude of my vector is 1. In other words, I'll just say I want the magnitude to be 1. Now, if we talk about the magnitude of this vector field, it's going to be negative y squared plus x squared. And let's suppose I want that magnitude to be 1. I get the magnitude of a vector field the same way as I always do with a vector, right? Square the x component, square the y component, add them, and take the square root. Now, if I square both sides, look what I get. I get x squared plus y squared equals 1. Now, what I've done, you'll see this inner blue circle here. What I've done is I went ahead and that's a circle of radius 1. Okay, in other words, I'm going to plot vectors from points that are on that inner circle. I'm just going to pick some of them, right? Now, I'll pick easy ones. So here's what I'm going to do. I'm going to take an xy, and then I want to look at the negative yx because that's my vector field, right? Or that's how I evaluate it. Okay, so let's look at this. Let me first of all pick an obvious one, 1, 0. Okay? So 1, 0, that means I'm starting right here at this point, 1, 0. And now I plug it in over here. So I'm going to take the y coordinate, put it here. The x component, put it there, so that's 0, 1. Now, I kind of messed up on my notation here. Really, it's a vector, right? Okay? Y'all see that? Now, it's confusing a little bit because you're taking the y component. This says take the y component and put it in the x position there. So don't let that mess with your head too much. But I've got a vector like that. Okay? Now, I can do the same thing. I can say, oh, I enjoyed that so much. Let me do 0, 1. So if I do 0, 1, then I've got negative 1, 0, right? So at 0, 1, then it says go to the left 1 and don't do anything on the y. So I've got that. Okay? Now it looks like it slopes up a little bit. That's just my drawing. I messed up, right? Y'all see that? Now you can keep going. Let's plot some other points that we might enjoy equally. Maybe I'll do this. Maybe I'll do negative 1, 0, and maybe 0, negative 1. Okay? So negative 1, 0, what would that be? So I have a 0 and negative 1 right there, right? And I could go ahead and plot that one. Okay? So negative 1, 0, that's right there. And then it says go down 1. Okay? Okay? Does everybody see that? And then one more just to finish it off. I've got negative, I've got positive 1, don't I? Part of the reason I chose this one is just because it's kind of, you got to kind of keep your head on a swivel. If it's negative 1, when I put it in there, it takes the opposite. So then I get this. There it goes. Does everybody see that? Now, we could do the same thing for, I could say, well, now I'm going to plot some vectors of magnitude 2. So I could do this. I could set this equal to 2, and then we would get x squared plus y squared equals 4. Okay? And then I could plot some vectors of magnitude 2, which I could plot this one, right? I could plot this one, and this one. I think it would turn out that way, wouldn't it? Okay? So if I pick 2, 0, I guess it would go that way. So you can see, so this kind of gives us an idea about how this vector field behaves, right? By looking at that, we can get an idea. Now, if you want to look at a more complete vector field here, let's look at this one. I mean, you can, if you just Google vector field plotter, you'll see where you can plot some vector fields. So here's a vector field here. Okay? Any questions about that? So you can see they've plotted a lot of them, right? A lot of points. Any questions about plotting these points or how we deal with these? Okay. Now there are lots of kinds of vector fields. Now, just as we're going along, let's pause a moment and think about how what's involved when we study vector fields. I mean, what kind of questions are we trying to answer? What kind of things are we trying to model? One of the things you could think about if you're talking about an R2 vector field is maybe if you're looking at the surface of a stream, right? And water is flowing down this stream. Well, some things that you're interested in is, well, maybe does the velocity, let's suppose you drop a leaf in the water. You might be interested in the idea, does this leaf accelerate? Is it getting faster and faster? Is it slowing down? I mean, I use a leaf. It could be a particle going through some other kind of field. But if you're looking at a stream of water, you might be interested in, what's the velocity of the leaf? Is it increasing? Is it decreasing? What's it doing? Another thing you might be interested in is the leaf just floating down, keeping its position? In other words, or is it spinning? Maybe is it spinning in the water? Well, that tells you something about the vectors, right? The differences in the velocity in the water if the leaf is spinning. So there are different things that you might be interested in if you're just looking at the surface of that water, right? If you think of it as a vector field. Okay? But anyway, let's go over here, and we're going to look at some properties of vector fields. Now, the first thing I want to look at is this idea of, we're going to classify vector fields. The first classification we're going to look at is a vector field being conservative. We're going to decide, how do we determine if a vector field is conservative? Now, first of all, I have to tell you what a conservative vector field means. This right here is not a vector field. This is a scalar function. Now, what I want to do is I want to take the gradient of this scalar function. That's what I want to do. I want to take the gradient of it, and remember we use the del, right? And we dot product that with the function. Now remember how this goes. If we want to find the gradient, we're going to take the partial, and this would be I, partial with respect to x, I, partial with respect to y, j. This would be the gradient. Now I want to do that here. So I'm going to take the gradient of this one, and I take the partial with respect to x. Okay, the partial with respect to x is going to be 2x y cubed I. And now the partial with respect to y, which is going to be 3x squared y squared. Okay, there it goes. Now, this right here, yes, ma'am. This right here is a vector field. Okay, it's a vector field. So notice we've got this vector field. Okay. Now, notice we got this vector field by getting the gradient of this thing, right? So we could say this is a gradient field. Okay? So this is a gradient field. Now, every gradient field is a conservative function, a conservative vector field. Okay? And we call this function right here, we call this the potential function. Okay? Now, if you have a gradient field and there is some potential function that you can, or if you have a vector field, if there is some potential function that you can take the gradient of and get your vector field, we say that vector field is conservative. Okay? In other words, if this bad boy exists, then we say that vector field is conservative. Okay? Now, we need to be able to find a test for determining if something has if something is conservative or not. In other words, we need to be able to be given a vector field and know with a simple test, is this a conservative vector field or not? That's what we want to be able to do. Because it's not always so easy to try to find a potential function. You know, it's going to, as you can imagine, it would require integration. Now, I want to show you a test, and then I want to show you why this test works. Let's suppose, so let me skip down here a little bit. Let's suppose we have a nice, handsome vector field. And let me just, just generically, I'll call it Mn, right? Okay? Now, let's suppose that this vector field is conservative. In other words, we know that f of xy exists, such that the gradient of f of xy indeed equals this thing. Let's suppose let's just start that is the given. What we want to do is say, okay, is there anything that is necessary for that to happen? Well, let's see. What we're saying is we're saying that f, the partial with respect to x, we're saying that that equals m, right? Definitely. Okay? Now, look at this. That means that the partial of that with respect to y is the partial of this with respect to y, right? I just partialed with respect to y on both sides. Okay? That's pretty clear. Now we could say, okay, what about the partial with respect to y from the initial function? Well, that's got to equal n. That's got to be the case. Well, playing the same game we played earlier, the partial with respect to x then would be this, right? Does everybody agree with that? Now, remember that these two bad boys right here are equal to each other. Okay? That's true. That means that if you have a conservative vector field, this is what has to happen. Notice that these two are equal, and so here's what this means. The partial of m with respect to y, which is this, has to equal the partial of n with respect to x, which is this. Okay? So this is a simple test that we can do. If you want to know if a vector field has a potential function, then you do this test. If that happens, then you do have a conservative function, and then you can go and seek out the potential function. Now, let's do that test on each one of these. Okay? So I'm going to do it on this one first. Now, remember what it says. It says the partial of m with respect to y. So I take the partial of this x component with respect to y. So let's see what that's going to be. This one is going to be x squared. Okay. Now let's do the partial of this with respect to x, and that is y. No. That's not a conservative function. I'm thinking that this little fella does not have a potential function. There's nobody's gradient that is him. He's nobody's gradient. Okay? So we already know there's no point in trying to find that. Now, let's go over here and look at this one. Let's do the partial of this with respect to y. Well, 0. The partial of this with respect to x. 0. Those are equal, right? Okay, well, then let's start trying to find that potential function. And really, it's going to be a matter of looking at two things. Let's look at this. We know the partial of this potential function with respect to x is equal to 2x. Now, that means if you integrate that, remember we're going backwards here. If you integrate, then that means that you have x squared plus some function of y, right? It's a constant, right? And if we're integrating with respect to x, then you have x squared plus some function of y, right? Now, let's integrate the other one. So we know that f partial of y is going to be y. So if we integrate that, what do we get? Well, we get 1/2 y squared plus some constant. And I guess it would be respect to x, wouldn't it? Okay. Okay, so we kind of put these together. So we have a function with respect to x here. We have a function with respect to y. So let me just put these together. And I get this. I get x squared plus 1/2 y squared. Now let's see if this is the function that we're looking for. If I take the partial of this with respect to x, I do get 2x. See, there's the 2x right there. And then if we take the partial with respect to y, I get a y. So yeah, this is the potential function. See, I'm just integrating each one of those and then looking and saying, okay, the integral with respect to x of this 2x is x squared plus some function of y. Well, here's my function of y right there. No, because all we're trying to do is find a potential function, just one. That's all we care about, so we don't need to do the plus c at the end. Okay, any questions about that? Okay, so we have this, we found this potential function. This did not have a potential function. Now, let's look back up here at this one here, just to kind of be sure we understand what's going on. If I want to find the potential function, or if I'm told, find the potential function, well, I need to know if it's conservative or not. So I'm going to take the derivative of the x1 with respect to y. So if I take the derivative of this with respect to y, I get 2x. The derivative of this one over here with respect to x, I get 2x. So yes, it's conservative. I can go ahead and try to find my potential function. So now I've got this, 2xy, okay? If I integrate it with respect to x, I'm going to get x squared y plus g of y, right? Okay. Now, I'm going to do the same thing with with y. Okay. Same thing with y. And I get x squared minus y. Integrating with respect to y, this time, I'm going to get x squared y minus 1/2 y squared plus k of x, let's say. Okay, did I do that right? X squared y minus 1/2. Okay. Now, what you look for is, you look for ways to kind of combine these at this point. And I notice this is always a good sign. In both cases, I have an x squared y. But what about this? Well, I have this. So it looks like that's my potential function, right? So I can say, okay, my potential function is going to be x squared y minus 1/2 y squared. And there's an infinite number. You could add, you could always add constants onto that. Okay? So this is my potential function. That's how you find the potential function. Okay. Any questions about that? Now, I've got another one on here that's in 3 space, but I think, so let me go ahead and work through it and see what we get. let's just look at the first one. Okay, so I've got this is equal to 2xy. The second one is equal to x squared plus z squared. And the third one, 2yz. Now, if I integrate with respect to x, I get x squared y. And I'm going to say plus some constant. I'll just leave that constant stuff off. We'll see if we can do it without it. Now, over here, I'm going to have x squared plus, whoops, I needed to put the y on there. Okay, so this is going to be x squared y plus z squared y. And now, over here for this one, with respect to z, it looks like I've got yz squared. Okay? So we're kind of streamlining it here. I'm not being very careful about my constants. But let's see if we can put them together now. It looks like I'm going to have x squared y plus z squared y, right? I mean, that seems like a pretty obvious grouping, right? Now, let's see if it works. The partial with respect to x is 2xy, check. The partial with respect to y is x squared plus z squared, check. And the partial with respect to z, the partial with respect to z is 2yz. Yeah, it works. So it looks like that is my potential function. Okay? Any questions about that? Now, in a minute, you might say, well, how do I test to see if that, in other words, how do I test that to see if it's conservative? We're going to look at that in just a second for the R3, but I'm going to include that in a different place. Any questions?